create this. So, and I'll be posting versions of it during the day. The time unit of this model will be in days. Okay. So with statistics and sensitivity analysis. Okay. This is going to be version 1 I'm going to create. Okay. So it should be time unit days, and we are going to rehearse how we go about creating a model of contagion, because it was mixed in with GIS yesterday, which gave it extra complexity. Okay, so here we go. Okay, so ladies and gentlemen, we've just created this empty new model called this. I'd like to now add an agent class called person. So we're going to do new agent type person with a capital P. Okay. Next, we're going to give that person an appearance. We've been dealing with different types of appearances. We're going to go back to an old favorite with the presentation. We're going to put in an appearance that is an oval. Okay. And it's going to be an oval with radius 10. Okay, 10. I use the properties to do that. Selecting the oval, you can go to the position and size and set the radius. Others of you may wish to adjust it manually. Okay. So within the very first part of this, we're going to build up this model, and we are going to do a couple very familiar or very, very common things when building contagion models. Okay. Next, I'd like to give this person an income parameter. Okay. So we're going to characterize their income. To do that, we'll go to the agent palette and drag in a parameter called income. What sort of type will that be? Double is right. Okay, great. Next, we're going to set the default here for that income to be a draw from a log normal distribution with a mu, that's the first parameter of 11, a sigma of 3.0, and a minimum of 0. Okay, so it's log normal of begin paren 11.0, comma 3.0, comma 0.0. Okay. Next, I would like to we're going to set it so that they're laid out in space, okay, according to the income. So we're going to go to main. And what do we need to do before we could run this model and show a population of these people? Yeah, we have to create the population. So in main, we'll drag in person here to become a population. I'll call it population. But is that everything we need to do to make it a population? Make it a population of agents. And we're going to add a parameter called population size that's going to be the size of this population. So we'll drag it here. It'll be called population size. Okay? What sort of parameter will it be? What type? Int is right. And its default value will be 250. Okay? Oops, 250. That's if we don't specify it somewhere, it'll be 250. Great. Okay? Next, we'll set the population to have a population size of that. So we'll go to the population and set the initial number of agents to be this dot population size. The final thing we'll do before testing this model, we've already gone on a little bit far. The second thing we'll do is, or the final thing we'll do here, is in the initial location, we will say at the specified point, and we will set the x coordinate to be, and I'll have to be quite careful about this, to be income divided by 100.0. Okay. I think I'm departing a little bit from script, and I don't trust my mental calculations about this. Let's just make it income, and we're going to change the income distribution to, instead of being 11, I was adjusting that in my head. Instead of being 11 and 3, it's going to be 6 and 2.0. It all just works out that we can lay people out with appropriate incomes directly that way. So I'm just changing the log normal up here. I'm not going back to the default. I could for the parameter, but I'm just changing the income here to 6.0, 2.0, and then the x is just going to be given by income. The y is going to be given by draw from. Oh, actually, sorry. Can we just say income? What do we need to do besides income? Self.income. Thank you. My income. Well, the income of the person about to be created. And for the y, we'll do it between 0, uniform between 0 and this dot space height. So in other words, we'll distribute them vertically between 0 and the height of the window. Okay? Or the height of the space. Okay, great. Excellent. Okay, so now I'd like to build the model, make sure it runs. TAs, be prepared here. Okay, so who needs TA help? TA help? Okay, so let's run this model. Okay, what should we see if we run it? Anyone? We'll see something like this. Do you see that? Okay. So these people out here to the right, who are they? These are rich people. And if you right click and drag, you'll see it. It's a long-tailed distribution. Okay? Okay. Okay, next, ladies and gentlemen. We're going to go now take a radical departure. Okay, so we're going to go to person. We're going to add in, blue. We're going to go add in, ladies and gentlemen, a network. Okay? And I'm going to show you something that will clue you into what's going on, and a common mistake that I'd like you to be able to avoid, because this is not an infrequent situation for my models. So, ladies and gentlemen, I'd like you to go to person, and I'd actually like to change the oval size. We set the radius to be 10, but I'd actually like to set it so that the radius rises with the number of people to whom a person is connected. So how am I going to do this? I've selected the oval. How am I going to make its radius rise with the number of people to whom I'm connected? Okay. Yeah. And suppose we do that. Can we start typing code here? Okay, this dot Okay, it says invalid number. What do we need to do?
Dynamic.
We have to make it dynamic. We have to say this, right? Okay. Okay. So the radius will be 5.0 plus, we'll make it 2.0 times this dot get connections number. I'll put it up on the big screen. There it is. Okay? So we're going to have some minimum radius, and then depending on how many connections we have, our radius will grow. It'll grow by 2 units for each new connection we have. Okay? Okay? So, ladies and gentlemen, next, I'd like you to just run this model and see what happens. You shouldn't see anything too different from the last one. This is just as a sanity check. Okay? You run it, and what you should see is something like this. Do you see that? Okay. So people are smaller. Okay, we don't have connections yet. We're going to in just a moment. So I'd like you to go to main. And in main, if you scroll down, this is the thing for which I was fruitlessly looking yesterday. It seems it was removed by AnyLogic, as best I remember. So, from the GIS context. So if you scroll down in main, you'll notice that there's a thing called network type. Do you see that? I'd like you to change that from user defined to distance based. And I'd like you to set a connection range of 250. Okay? So we're declaring, let there be a distance-based network imposed on the individuals who are already situated in space. It's applied at startup, and any 2 people be connected if and only if they lie within 250 units of each other. Are we okay with that? Yes, John.
What is the unit of the range?
The unit is with respect to these visual units, but they have a corresponding distance here. Do you see that? Yeah, and so you can actually set this distance metric to, see it says here, ruler length corresponds to so many meters, but the actual length of this 250 is with respect to these pixels here in the underlying system. So you notice as I'm clicking around here, there's down here in the lower right, it tells me what what the conversion is. 1 meter is 10 pixels. And here, this is at 50 pixels. See, it says 52. There's this little, see it, it's moving, that X? And this is 100, okay? So 250 is going to be somewhere up around here, units, okay? 2 people be connected if and only if. And you could translate that into appropriate 10 meters, but you could also change the scale, okay? So great question. Okay, ladies and gentlemen, let's go now run the model. What do you think we'll see now? Will everyone be the same size? Okay, what do we see? What's going on here? Why are some people so much bigger than others? They have more connections. The further you go out to the right, the fewer connections here. Okay? People are spread out more. There's less crowding. Okay? Okay, now, did you see a network? No, but there is one. That's the important point. There is one there, and I want to show it to you now. So there's a difference in any logic between there being one, there was one, people were connected. That's why some people had more neighbors than others. In order to see it, you need to go to person. Don't be confused. In Maine, one not infrequent student misunderstanding is there's connections in Maine that people try to deal with. Those aren't of interest here. The connections in person are the connections from person to person. You want to go to the connections in person. You may have to scroll up a bit. I'd like you to go indicate that these connections are to be displayed here, okay? You'll notice there's several areas of it. And one thing that's a little bit confusing is you can't even see it clearly, that area called animation, because communication in mine is blocking it. But if you collapse this, you'll notice there's communication. You want to check this box that says draw line connecting agents. Do you see that? Okay. I'm going to ask your pardon to do one other thing as well. I'm going to indicate here agent type person, meaning people are connected to other people, not just any old agent. Okay? They're connected to other people. Okay. So I'd ask you now to run this. Okay? Run this model so that we can see the results. Sure.
Does it automatically know to talk to the automatic network? Because if you have more than one connection, so you can drag in more connections,
Yep.
right?
Yep.
Is it that first one
Correct.
that talks to the automatic network
Correct.
that's set up?
Precisely.
Okay.
Precisely.
And then if you drag in more, then you have to define the networks for them? or-
That's right. So it's a good question. Unless it was unexpectedly changed in 8, which I don't believe it has been. We've been bugging any logic about this issue. We're trying to make these other networks, ideally things that could be auto-configured. But really, this sort of auto-configuration, setting up a distance-based network that we requested through Maine, that applies very specifically to the first set of connections associated with people. If we dragged in an IDU network to accompany this, and it was called IDU network, that would not be configured by Maine. And we would need to set that up on our own. Now, Cheryl, yes, I believe that's, so, okay, I'm 98% certain of that. There's some thought in my mind. Is that a Winchillian head back there?
Yeah.
Okay, Winchill? So, okay, I want to ask, I got 2% residual uncertainty about something. The automatic network configuration from Maine, that you can do from Maine that will configure the distance, you say this is distance-based. That applies, certainly through the interface, it applies to this set of built-in connections with a person. If you add additional connections, is there a way for any logic to be told auto-configure these to be a small world network or a scale-free or a distance-based?
The only thing you can do is you apply a network to have the newly added agent to apply the network. Like if you click, basically there's a check say apply on startup.
Right.
If you check that, it's basically that only applies on
Sure.
those agents that exist before the model startup, which like you initially said you should have.
Sure. So that's true, but actually the question we're asking, Winchell, so that's worthy comment. But the question we're asking is a little bit different than that. The question we're asking is if we had for a given person multiple types of networks, say an intravenous drug use network, a family network, a collegial network.
This one always working on the standardized link, which is the default link, which is always like a bidirectional.
Okay, but the question is, can we tell any logic for the IDU network, use a distance-based network. For the family network, use a.
You have to do the manual.
You have to do it. That's what I thought. You have to set them up, add connections manually.
Yeah.
Okay. My uncertainty has gone from 2% to, with Winchell's input, 0%. So yes, we have to. The other ones, this initial set, that's the one that you could tell any logic, configure it with this type of network or that one or that one. And you can, by calling apply network, you can get it to be reapplied.
Yeah, but the apply network is pretty inefficient. It
Yeah.
will disconnect all the.
Exactly, it recomputes the entire
Yeah,
network.
you can't do
Yeah.
additional. And FYI on this guy is another comment on this is like this only apply to the agent that lives directly within this environment. So
Right.
if you have agent live in the sub environment of this environment,
Yeah.
that doesn't work.
So-
it doesn't work for hierarchy.
Right. So for example, if you have a hierarchical model where you have cities within Maine and then neighborhoods within cities and people in the neighborhoods, the thing that affects their network is the thing in which they're immediately embedded. Now you can always do these things manually. You can always add the connections. There's no problem there. It's just that you can't get it to auto magically configure it. For that, it's the connections. Okay.
Thank you.
And okay, very good. Thank you, Winchell. That's great. Okay, so here's our network, and you can see it's now visible. It's visible because we enabled it, and people have different sizes because they are have different degree centrality, as we say. Okay. Okay. Next, ladies and gentlemen. We have a static network. That's interesting. It could lend itself to some interesting analysis. We could do a scatter plot, for example, looking at income versus connection count. That might be kind of an interesting thing to do. But time is a burden, and a buffet will soon beckon. So we have to make progress, okay? So the next thing we're going to do is we're going to go add in to this person the capacity to have a network spread of infection, okay? We're just going to rehearse that because that was done yesterday in a GIS environment, and where setting up the network was more difficult, and I don't want it to be obscured. I want to hit it at least one more time, and that's this time. Okay, so I'd like to drag in a state chart entry point. It'll be called infection state chart. This could be infection. It could be attitude. It could be knowledge of a rumor, or it could be attitude towards an innovation, whether you're an adopter yet or not yet an adopter, etc. Whether you're skeptical. It could be with respect to spread of attitudes with respect to vaccine hesitancy. Someone who's neutral, someone who's who credits vaccines with their effectiveness, someone who's skeptical, someone who's hostile, something like that. And there may be spread of memes. So infection state chart here, we are going to have simple, susceptible, and for quickness of delivery, we're then going to have a state of infectious, and we are going to have a recovered, which is going to be temporarily immune. So I'll say recovered, and then they're going to go back to susceptible. Okay, so ladies and gentlemen, having done that, I'd like, based on the learning from yesterday, I'd like you to try, well, okay, I'm going to, this will be an interesting little exercise. It's too bad Jeff, there's Jeff, he can watch this. Ladies and gentlemen, I'm going to do one final thing, and then I'm going to challenge you to fill out some elements of this. I will do so with muted video, and I will show you my solution. But I want to see if you can put yourself through it. So the other thing I'm going to do is I'm going to add into the model a messages thing. And in this messages, there'll be a message exposed. Okay? Exposed. Great. Okay. So, having done that, I'd like you to fill out the balance of this, reflecting the fact that individuals, okay, we're going to, just to show how we can do this, do another point of learning. I'm going to add into main a parameter that's called probability, and it's called transmission probability. So given exposure, you have a certain chance of getting infected. I'm actually not going to ask you to use this immediately, but we're going to come back to it. Those who are more advanced among you may want to use it immediately, but otherwise we'll leave it there, and we'll introduce it in after I show you my solution. I'd like you to have a mean recovery time, so I'm going to drag into main a parameter that's called mean recovery time, and that is going to be 10 days. Okay? Incidentally, you notice that it's type. We say mean recovery time, but it's just type double. We could actually specify a time, that it's actually a time, and specify that it's in days, for example. Okay? And that would actually make it especially clear, say, to a stakeholder that this is measured in a certain number of days. So it's not just 10, it's 10 days. Okay? Be aware that when I last checked, it didn't automatically do the conversion. If, like, you specified in minutes and your model's time unit is days, I don't think it was automatically doing the conversion between them. So it's more for documentation that we say 10 days. But hopefully they've changed that by now. And then I'd like you to have, beyond mean recovery time, I'd like you to have a mean duration of immunity. So that'll be a time till waning of 30 days. Think gonorrhea or possibly chlamydia. And here we might do days. Okay? So 30 days. 30 days. Great. Okay? So there's going to be a mean recovery time, mean duration of immunity. Well, I was going to ask you to do this on your own, but maybe I'll just interactively ask. So tell me where the connections should go. When should the connections come, and whither will they go? Give me one connection that needs to be there. One transition. Sorry? Susceptible to infective. A key one. Good. Okay. Excellent. And what sort of transition will this be? Will this need to be? Okay, it could be a rate, but if we want to capture a situation where others around you being infected is a risk factor for you getting infected, a rate wouldn't capture that. A rate would just be, regardless how many people around me are infected, I'm not going to get infected. It's a message transition. Good. What message will it be? Exposed. Oops. Exposed. Not in quotes, just exposed. Where does it know about exposed? Whence did that come? Option list, indeed. Okay, tell me another transition. Infectious to recovered. Good. Okay, now, you notice I specified in main a mean recovery time. If I had named it better, it would have been mean recovery in days or something like that. By the way, I'm gonna show these. I'm gonna give them names. So the first of them was infection, show name. The next is recovery, show name. And we're going to have this recovery be dictated by this mean recovery time, okay? We could just make it a timeout after that time. I'm going to make it a rate of 1.0 divided by that mean recovery time. In both cases, and because that lives in main, we have to say main dot mean recovery time, okay? Like that. Is that okay? Okay. So to go from here to here, that will be catalyzed by a message. To go from here to here, they'll have a certain chance per day as 1 divided by mean recovery time, or 0.1 chance probability per day of recovering. It's a hazard rate. Next, where's the next transition going to go? Recovered back to susceptible. Let's build up these skills. So we're going to go like this, and we're going to go like this. Okay? There we are. Great. And this one is going to be called, I'll call it waning of immunity, and I'll show the name. Okay? There we go. And it will be a rate-based transition as a rate of, well, you know what? Maybe we'll make this a timeout just for a bit of diversity. And what will the timeout be? Main dot, 30 days, but it'll be main dot duration of immunity. Why would we, main dot duration, or mean duration of immunity. There we are. Why would it be that we specify it in main? Why not just hard code it as 30? By specifying it as a parameter, what benefit do we get? Yeah, we can more easily modify it from scenario to scenario. It's documented what it means. So if we just said 30, it might not be obvious. Maybe we have one parameter that depends on another, or something like that, and the meaning of it is clear. We can go to that parameter, document where that number came from through the description field. You notice AnyLogic supports these description fields where you can document things. And we have one place where we can change it, and maybe it's used in several places. You can have an output for model metadata for the results of the model. It could describe the assumption about this was such and such. The assumption about that was this other thing. So there's lots of good reasons. Okay, so now we have, going back. Notice this model is different from yesterday. Yesterday we had treatment-mediated infection. Treatment-mediated recovery. Here we have recovery that takes place after a fixed time we have recovery that takes place according to a hazard rate, and then we have waning of immunity that takes place after a fixed time. Okay, so we have basic mechanisms in place for natural history of infection. What do we still need to do? What do we still need to do?
Send messages.
Yeah, we need to send messages. Where should that be located? Well, okay, there will be one in main. That's a good point. But where else, for the infection to be transmitted, where does that transmission need to happen? Yeah, the infectious state here needs to have a transition that will go off. This will fire without leaving the state. It will fire and we'll have it do so with a rate of every 2.0 per day. Okay? Do you see that? 2.0 per day. Now, what will happen when that fires? What will need to happen? They send a message. Good. This dot send to random connected a message exposed. Okay? Note, they will not leave the state like this in this case. If you want them to leave the state, which, like if you wanted to recompute something about their chance of leaving or something, it actually needs to go out of the state and come back in. We did that one of the earlier models. This one stays inside the state. So this one actually doesn't leave the state. It just fires whilst you're in the state at an average rate of 2.0 per day, 2 times per day. Okay, ladies and gentlemen, we're just about done. John mentioned the final thing. What is it? Yeah, we have to have an event in main to trigger the infection for the first time. Okay. Now, we could do that. I want to ask if people would like to see a different variant of this, which is also common. In fact, I'm sorely tempted to do this. Okay? It won't take much longer. You've seen how to do the event to trigger things. In fact, I even gave you some code. In fact, I refined some code after the fact, which in that latest version of the model, to spread it to randomly n randomly chosen people. Here, we're going to start a certain fraction of the people susceptible, infectious, and recovered. Okay, so I'm going to introduce what's called a branch construct. Okay, so to divide people up initially between different areas, we're going to have the initial state here, and then we're going to have a certain number of people come directly into susceptible. That will be the default. A certain number of people come into infectious, and then a certain number of people come into recovered. Now, rest assured, I'm going to fix up this mess. Okay, so we're going to drag this out. Okay, we're going to drag this out here, like that. Okay, now a branch transition basically allows you to split up where people go into one of a set of possibilities. Sometimes that's done via roll of the dice. Sometimes it's done via a defined condition. We're going to here have it done according to a criteria for each person. Okay, so the first thing you should realize, though, is that these branch transitions, they have one default case, and then they have several condition cases. So these ones will be based on a certain condition. I'm going to change them to condition, and we're going to fill in their condition. Whoa! We're going to fill in their condition in just a moment. Okay? So these are going to be based on some condition, and this will be the default. People by default start as susceptible. Okay. Next. Winchell, is it true in any logic 8? I saw a hint in any logic 8 that the state names are now optionless.
Right. Yes.
How can I access the name of that option list?
You would use the state chart name dot
Thank you. Okay, ladies and gentlemen. Okay. So we're going to further watch this, Winchell. Winchell? So I'd like you to watch this, okay? Yeah. Okay. So we're going to drag in initial. We're going to have initial state as a parameter. Okay. Initial. I'll call it initial infection state. Are we okay with that? Okay, and we will pick. Okay, actually, are we going to be able to specify it, Winchell?
I'm sorry?
Are we specify the name of that type here?
Oh, you can say that.
Cannot.
Yeah, you can.
Okay.
Yeah.
Okay, so what would that type be? It would be infection state chart
Yeah.
dot.
Well, I think the type is infection state chart, because that's an enum, right?
That's an enum?
State is
Okay,
infection.
cool. You think so?
Yeah, I think so.
Okay. Okay, let's build this, make sure it's fine. This is a change in AnyLogic 8, which if it works is great. But
Auto completes.
Three keeps underscore dot state, the underscore state.
under
But
okay.
without the dot.
Oh?
Sorry, yeah.
Okay, so let's. Okay, cannot be resolved to the type.
I think you can try to person and then dot. It should auto pop.
Okay, person dot.
Yeah.
Okay, let's just try this. Sorry. Oh, okay. Yeah. Okay. There's an easy way around this, which. Oh, okay. Person dot infection state chart. Okay, now here's Winchell. This is 1 minute ahead. It's coming up soon. Sorry.
Yeah.
If I have a custom distribution set to be from an option, can I
Right.
choose that?
Yeah, you can choose, but still person dot something, because that's embedded.
Yeah. Okay. You sure? It'll be in the drop down. Okay, ladies and gentlemen, this is what we will have. And so what this is saying is we will pass in what state someone is going to start in. Okay? They're going to start here. They're going to start here. This is the clean way to do it if we want a certain fraction of the population. Do you see where I'm going with this, Winchell?
Yeah.
Okay, because I hope you and I both agree with AnyLogic 8 there shouldn't be a problem. I've never done it before, but what the hell. Okay, so here we go in main. Okay, I gotta have some fun in these events. Okay, so here's the custom distribution. This will be initial infection distribution. You sure, Winchell?
Yeah, because that.
Okay,
that's
option,
right?
but it's not listed here. That's the
Not
thing.
listed, you can specify.
You could still type it?
No, you can just say new custom distribution.
Oh my God. Okay, that's horrible. That's horrible. Well, okay.
Well, another thing you can, if you really want, import person, import static.
Okay. This is okay. I flew a bit too close to the sun on this one, I think. Okay. It's a nice idea, but AnyLogic didn't finish the job. They should have allowed you to pick this as an option.
Because that's inside the agent. So.
I know. They should at least let you type which option was to do it.
Yeah.
Mumble. Okay.
Yeah.
Okay. Fine. Okay. Well, it's still not that bad. We just have to do it the old way. Okay, ladies and gentlemen, this is what we need to do. Sometimes you win, sometimes you don't. The feature is not quite complete in AnyLogic 8, it looks like. Okay? So I'd like you to do new, add to the thing an option list. So it'll be called initial infection state. Okay.
Maybe it's just simpler to import it. Because you can, because the reason it is not visible is just really because it's inside a first.
Right.
And I think what it scans is like.
So how do you, you're saying you add the custom code to import it?
Yeah, you just import it in main.
Okay, why don't you go test if it works? Yeah. Okay. Okay. So, okay. Yeah, I like that idea, Winchell, but let's test it out before we test it on people. Okay. Clinical trial phase 1. Okay. Okay. Susceptible. So we'll say initially susceptible, initially infective, initially recovered. Okay. I don't like this. Winchell is hard at work on a better solution. I was hoping in any Logic 8 it would support it with a delightful ease, and he has an idea that would allow it to be at least moderately delightful, and is working on it. Okay, Winchell is a magician, and I wouldn't be surprised if he could pull it out of a hat. Okay, so this is an option list called initial infection state. By virtue of defining it as an option list, then we can have the beauty of it. The beauty is that now we can have the custom distribution for the people in the state to be drawn from the initial infection state. So maybe we want 90% of the people to be, or 50% to be susceptible. We want initially infective to be 10% of the population, and then we want the balance to be recovered, something like that. What do you think? Is that okay? So this is a distribution. Now Winchell is trying something amazing, and it may work out. Okay? Okay. Next, we're just about done. Just about done. Here we're dividing people up into their initial state. This is a general pattern. This is nothing specific to infection state. You could do this for chronic disease. How many start at each stages of a chronic disease? That's the importance of this pattern. In contrast to sending the initial message, which is quite specific to infection. Here we're dividing people up into initial states. Okay, so back to person. We will set this initial infection state to be other, and we'll set it to be not other, we'll set it to be initial infection state. And the elves are hard at work. Okay. And finally, for each of these two transitions, we will test if this parameter equals the associated thing. So we'll test for this one, this outer one, does this dot initial infection state equals initially recovered. Boom. Okay? Just like that. For this other one, we will test if this dot initial infection state equals initially infectious. Initially infective, I called it. Okay? And that's it. That's it. So, a certain fraction of the population will start in each of these states. 50% will start susceptible, 40% will start recovered, 10% will start infectious. A given person will be told ahead of time where they start, and now we just have to complete the final thought. Where do we tell people where to start in the population? Initial infection state, what are we going to do to figure out whether a given person starts in one or the other? We draw from the distribution. So for each person, it will figure out what state will they start in. It will tell them which one they'll start in. At the person level, they will be told, you're going to start in this state. when they come in here, they'll therefore go to the appropriate state. This state, or this state, or this state.
Question.
Yeah,
With the branch, when there's 3 options.
yeah.
What if the 2 of them are true? Is there a priority that's obvious, or it doesn't happen in this case?
Right. Yeah, so if they had overlapping conditions. So I actually don't know the answer to that with certainty, but I'll hazard a pretty good guess based on how any logic works elsewhere. And it's a guess that I don't like, but I don't like the answer, but I think it's probably the case. Wind chill would probably know. Wind chill?
Yeah.
So here's my guess is that the branch you added first, chronologically, to the model will be the one that takes precedence. But so the question was, suppose that there were 2 conditions, both of which were true. I think it probably goes in the order in which you added them to the model.
Yeah, I would also plan on
Yeah.
having tested. Well, the test results is that you can select it from the drop-down list, but you can't create it.
Okay,
Because we
you
create-
could create it manually.
Yeah.
Yeah, okay, yeah. Thanks, that's very helpful. Okay, so maybe we could put in something to any logic request to have them let you pull down the option list. Okay, great. Ladies and gentlemen, let's build this. Let's make sure it works, and let's run it. Well, make sure it compiles, and now let's run it. So it thinks it understands it, now we're going to run it. Okay, here we go, boom. Oh, are people infected? Let's go take a look. Okay, this person's susceptible. This person's infectious. But why aren't we seeing visually? Yeah, so should we add that color? You know how to do that. Let's go at it. So this is sort of rehearsing your skills. Okay, we're gonna have a variable, and that variable is gonna be color. And what type is it gonna be? You know the shtick. It's gonna be other color. It's going to be initially, let's make it black. If you want, you can make it initially purple. Okay, black. Okay, you know how to set it. Susceptible. Oops. This dot color equals green or lime. I'm going to make it lime. I'm going to further pull this color so it's self-documenting. Next, for infectious, this dot color equals red. I'm going to pull down red. Next one, this dot color equals gray. What do you think? Sort of burnt. Is it AY or EY? AY. Okay, thank you. That's silver. This is gray, I think. Yeah, okay. Great. Okay, ladies and gentlemen, have we finished, though, the color? What final things needed? Yeah, we have to connect it to this guy. We haven't completed the thought, really. Okay, so we'll have fill color. How do we choose that we want it to be defined by a variable? What do we do? Yeah, we have to test it to be dynamic, and we have to say this dot color. Okay, we're done. Let's go run it. Here we go. Run. Okay, and we can speed it up. We can have it run full tilt, which you do via this, okay? So here we see the infection moving around. It's running so fast we don't even see the connectivity, but I mean from one time point to the next how it's spreading. there's also these big occluding features of it. But over time, some people become susceptible again. They lose their immunity. They get infected. They then transmit it to other people, and round she goes. Okay? Okay. Now, our interest here, though, is a little bit different. We're going to be using this model. So I will save this, and I will provide it to you. Okay? I'm going to provide this to you as part of the models built-in class. So if anyone wants to go get it, you can do so in just a moment. Here we go. Boom. Hey, come on. What the heck? Okay. Here we are. Okay, and I'm posting it. Okay. Okay. So it's called SIR with statistics and sensitivity analysis. So now let's let it live up to its name. We've got the SIR. Let's do the sensitivity analysis and reasoning about the statistics involved. Okay. So, ladies and gentlemen, what I'd like to do is to here go back to this model. It's posted. And I am going to go and I want to summarize how many people in the population are infectious. How am I going to do that? Can anyone tell me? Where would I go? Sorry? Statistics. Where do the statistics live? Population. Okay. Great. Great. Okay. So in population, we can define a new statistics. Right now it says no items yet defined, but we could define one here, and that we will do. Okay. Okay. So we're going to do plus here, and we're going to call this count infective. And what type will it be? A sum, an average, a min, a max, or a count? Count. Okay, now do you remember how we specified the condition? What are we going to ask about that person? Are they in what? A certain state, to wit, the infectious state. So we're going to go back to that statistic, and we're going to ask, are they in the infectious state? Is this person? What is the person's name? Item dot in state. We're asking, are they in a state? And the state is going to be person dot infective. Okay? Person dot infectious. Sorry, I called it infectious. Okay. Okay. Great. Okay. Are we okay with that? Okay. So let's run the model and let's observe the dynamics of that just very briefly, make sure things are hunky-dory, and we will then proceed to do a little graph of it. So let's run it. If we want to do this, if we want to access that statistic, where can we go to access it? Yeah, we can go to the population here. And here, count infective is 84. Count infectious is 75, 64, 49, 48, 53. Okay, so it's evolving over time. Great. Great. Now suppose we want to have a, I think of the best way to do that. Suppose that we want to have here a, right. Suppose we want to have a time plot that shows this over time. How do we do that? Yeah. Okay. So let's go let's go find analysis. We'll drag a time plot. And in the time plot, we will go, we'll call it prevalence time plot. And we'll add a value. It will be called prevalent case count. And the value will be this dot population dot count infective. Okay, that's the statistic. It'll be updated recurrently once per day, and right now it says to save up to 100 of them, and that will be fine for now with a time window of 100. Do people need me to show anything from this? Are you okay with that? Okay, let's run this. Okay, my chart lives further up here, and you notice it's coming up now, and it's scrolling over. It seems to exhibit some variability. You'll notice it's going down to about even 20 sometimes, and it's going up to about high 60s maybe, commonly up, and sometimes above that. Do you see that? Now, if you want to have more continuity in the chart, within this chart, if you select it, you could tell it to display up to, say, 1,000 samples, 1,000, and it'll be a time window of 1,000 model time units or days. Okay? Why don't we do that? But more than that, and this gets into a very important issue I wanted to cover in this session. If we go to the simulation, ladies and gentlemen, you'll notice that right now the simulation says stop never. We're going to change this to stop at the specified time, and it'll be a stop time of 1,000. So what did I just do? I did two things. I went to the chart, and I set the chart to display up to 1,000 samples with a time window of 1,000. And then I went to the simulation, and I set for the simulation to run to stop time 1,000. Let's run the simulation again and see what results. Okay, here we go. Okay, so I'm running it flat out here. Okay, it's time 1,000. Let's go up, and what we see is some initial very large swings, and then some and then sort of a period where it's oscillating less and less pronounced way. You notice that there were very large swings initially. But one thing that's notable is there's some regularities here, it seems, but it also seems like some noise. And I want to ask this question, and again, this is a key question for this next step. Ladies and gentlemen, this simulation, if we go look, we see that it's actually, if we run it again and again, we'll see the same results. It's actually running what's called a fixed seed. It's running the same exact sequence of random numbers, which means the exact same people get infected at the exact same time. If we want to get a sense of variability, we need to run it with a random seed. Do you see that? Random seed here. And there we can run it, and here we go. And we will see something a little bit different in its details. And there's a disconcerting question that comes up. What is the regularity here that transcends particular runs? Is there an order to this? Are these just flukes, these initial big swings? We've seen it twice, but how do we know how long it will go on? Maybe these 2 times we've looked at are not representative of the broad distribution. Maybe if you run 100 times, these will only occur 20% of the time. I'd like to suggest we move beyond the vagaries of always looking at a single run and move to a situation where we look at many different runs in turn associated with this, okay? So here, we will turn to the next stage of this model, where we are actually going to run this not once, but several times per experiment. Okay? Okay, so ladies and gentlemen, would you like me to distribute my current version of the model? Would that be useful? Okay, I will do that. I will put it up there. It will be version 3. Okay? Okay, who needs TA help? TAs? Anyone need TA help? TA. Who's the TA in attendance? So sector 2. Okay, sector 2, front. Who else? Who else needs TAs? The TAs have been on a low duty cycle. Okay. 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 Okay, so we're going to distribute my model. Here. Okay. Here we go. Hello? Okay. Why aren't I seeing this? Okay, models built in class. Okay, and let's try this. Here we go. Okay, it is there. Ladies and gentlemen, it's up there. SIR was statistics and sensitivity analysis. Okay? Okay, ladies and gentlemen, next we'll make the critical step. Who needs a bit more time though? Do you want me to hold? Okay. Who needs TA help? Okay. There's a TA giant who can raise his head if called upon. Is there anyone else who needs a TA? Okay. Okay, ladies and gentlemen, I've placed my model. Are you ready to go on? Okay? Okay, ladies and gentlemen, we'll now go where this class has never gone before. Okay? So we will right-click on the model. We will say add a new experiment. In the experiment will be a parameter variation experiment. Okay, so I did add new experiment, right-click, new experiment, and it'll called parameter variation experiment. Okay, maybe we'll call it something, well, sure, we'll call it parameter variation. Okay, but it's really designed to examine more than one run. It's multi-realization. And I'm going to choose parameter variation here. You notice that it's a little tick next to it. I'm not sure the semiotics, but that's what it has. Okay? We'll say finish. Parameter variation. Okay, now, ladies and gentlemen, a parameter variation experiment will allow us to run the model. So thus far, when we run an experiment, it will run main one time and show the results. If we want to run it again, we can do so, by running that experiment again, it will run main once. Now we're going to have experiments that run main more than one time. They run main several times over. And I'm going to walk you through the basics of this here, because we're going to use it for two things. One, to examine the effect of uncertainties induced by stochastics. Number two, to examine the effects of modifying parameters. So in the parameter variation experiment, we're going to have additional choices, okay? And we're going to have additional needs as well, okay? Okay, so what I'm going to ask you to do is to go here and in this parameter variation experiment, I'd like you to open up the tab that says parameters, okay? Okay. There we go. So I would like you in the parameters area, you will see a number of assumptions that we can specify in terms of how we wish to run this several times with respect to the parameters. We can either run it with parameters fixed, at fixed values, and have a certain number of runs, or we're going to be able to vary parameters over some range, in which case the runs are dictated to us. For example, we could have a two-way sensitivity analysis where population size goes from 100 up to 1,000 with steps of 100, and mean recovery time goes from 10 to 50 in steps of 10. And that would involve a certain number of realizations to be run. For now, we're going to start with freeform, and you notice by switching to freeform, we enable the number of runs. If you are varied in range and we vary these things, the number of runs is told to us. It's just how many are required to explore all of them. Here we're going to have freeform, and we're going to have, ladies and gentlemen, 50 runs, 50 runs. Okay? So it's going to run it 50 times over. Okay? Next, we are going to go and we will actually try running this just to make sure it runs properly. We're going to go run this and we'll see how we run it mechanically. Then we're going to go back and have it show us some information. Okay, so I have this here, and at first it doesn't seem to be particularly clear what to do. But this button is the button you want to use, okay? So if you do this here, it'll be running. And you notice it's running quite a few here. It's actually counting the number of runs. This is an indication that different cores on the computer are running it at the same time. So it's running in parallel. And it stopped at 50. Let me show that again. Here we go. Do you see this? Okay. And it's advancing here. I'm running it for another 50 now. But it was running it in parallel through that time, running it out to time 1,000 for each of those. But it can do so in parallel because they don't depend on each other. Okay? Okay. So, ladies and gentlemen, we ran this model several times. You may have noticed it's pretty fast. It's actually sometimes a lot faster to run it with a parameter variation experiment with a fixed set of parameters than to run it visually, because it doesn't have to deal with all the visualization. So sometimes we run parameter variation just to run it a bit faster and without the necessity of seeing all the output. But our goal here is a little bit different than that. Our goal here is to summarize over many runs what the results were. And in order to do this, we're going to need to take some steps. So what I'm going to do is to go back to main, and we're going to add in a mechanism to record the number of infective people for each day. Not just on the graph, but in a data set, which we're then going to be able to use. Okay? A data set is something which we can use to record data over time, or pairs of data. Here we're going to use it over time. Okay? So there'll be pairs, time, value for that time, value for that time. So we're going to go to main, and we're going to add into main a data set. Okay? Okay, and within this data set, you'll notice that there's several settings. By default, it keeps track of the the time for the horizontal value. I told you a data set consists of pairs, and what this is saying is the x value of the pair will be time. The y value of the pair, sort of the corresponding element to the pair, we're going to tell it to give us the count of people infected. If we wanted here for this data set to have the y value be the count of people currently infected, how would we get the count currently infected? We did it for the plot earlier. How can we do it here? What do we through the statistic, and how do we get access to the statistic? Where does it live? Yeah, this dot population dot count infected. Are we okay with that? Okay. Now, data sets are your friend. Data sets have many uses. Okay. And we're going to name this data set prevalent case count data set. Okay. It's going to give us the prevalent case count over time. You'll notice it says keep up to 100 latest samples. I want it to be 1,000. And it says whether to update data automatically. Yes, I will update data automatically every 1 day. Is that okay? Every 1 day we'll have this data be updated. Okay? So this data set's going to be spying on, observing the count of people currently infected and recording that within the data set. Are we okay with that? Okay, so let's go run this model. Let's go run simulation. Let's go run the single time. And I want to make sure that data set is working. Okay? It's living in main, and it should be recording things. It should have built as well. Okay? Here we go. So let's run this out full tilt. And you notice as I run it, it's accumulating things in the data set. If I click on the data set, it'll show me numbers over time. Do you see that? Now that it's finished, I would note that I can right-click on this and say copy. And I can then go to a spreadsheet of my choice, and I can do paste, and I will get out the values here. Okay? So I've just done this to Excel. You could do it in other packages. But fundamentally, this is recording the number of people who are infectious at different times. Do you see that? Do you see that? Okay. So the data set is a useful quantity. It's useful. We can do a graph here and see what it did over time. Do you see that? So with the data set, we can view it as this, or we can do a graph and see it over time. We can also copy and paste it into a spreadsheet, okay? So data sets are useful constructs on their own. It turns out that we can also output these to a file very easily. You can output them to an Excel file automatically, for example, okay? But our goal here is a little bit different. And I want to finish this step because it's a very important one. So ladies and gentlemen, we have this data set. I would like now, this data set, where does the data set live? Where do we place it? In main, indeed. I'd like now to go to the parameter variation experiment. Okay. Okay, now, in the parameter variation experiment, I would like to go and add in a few items here so that we can summarize the data coming from main over many, many realizations. Okay? Here, I am going to place into the parameter variation experiment from the analysis palette. I'm going to drag two things in. One of them is a histogram 2D data. Okay? And this will be called prevalent case count histogram 2D data. The other will be a histogram 2D, which is a chart. So one will hold the data for the chart, the other will be the chart itself. So the histogram 2D will be called prevalent case count histogram 2D. So one is going to be that long name data, one is going to be that long name by itself. Now, you'll notice for the chart, there's a data element here. Do you see it says data? What do you think we want to use for the data? We want to use the corresponding item here. So we want to use, to provide the data, this thing we already created, the data item here. So this will be called prevalent case count histogram 2D data, or this dot prevalent. So this 2D data chart is going to point to this data object. Okay? So all we did is we added each of those in there. One is a data object, one is the chart itself. This chart, we did add histogram data, and we referred it to, we told it, where's its data coming from? It's coming from this other thing. Okay? Are we okay with that? Okay. This 2D data object is going to summarize what's going on in the model, not just over one realization, but across many realizations. So we're going to be able to see what part is regular, what part is irregular. It's going to summarize for us the variability over many, many realizations. Does that make sense? Okay. Okay. So, now we have to complete the thought. Okay? In order to complete this, we're going to need to go back to the projects, go to parameter variation as a whole, the experiment as a whole. Notice I dragged those things into parameter variation. Here in parameter variation as a whole, I'm going to go down to this area called Java Actions. And basically what's going to need to go on is, each time this thing runs main, I'm going to need to extract information from main to save it away, because main's going to go away. I have to salvage that information before main disappears. Main is then going to disappear, the main object. But I've saved away the information, and then it's going to run again. And I'm going to save away the information from that run, and then it's going to run again, and I'm going to save it away again. Because I'm trying to summarize the results over many runs, so I need to store up information from each successive run to add it to my summary. Does that make sense? ladies and gentlemen, where is this occurring? Where is this summarization occurring? Where is this accumulation occurring? Well, it's occurring at one key place, after simulation run. Okay? And what we'll do there is we will say this dot prevalent case count histogram 2D data. That's the thing that's storing up the summary. That's the thing that's storing up, accumulating the information. And what do I need to add to it? The thing I'm getting from main, which is that data set. The data set, ladies and gentlemen. The data set in main. That's the thing that tells me what went on in each run. So before main disappears, I'm going to suck that information out of it. I'm going to suck out that data set, and I am going to go and store it away in my own 2D data set. So here we have a prevalent case count data set in main, and in the parameter variation experiment, I am going to take it out of main, and I'm going to stick it into this 2D data object, which will then be summarized on this chart. Okay? So how do I do that? How do I suck it out of main? Well, it turns out main is called root. I know, you can blame us. Okay. Computer scientists have weird names for things. Root. Root dot prevalent case count data set. That's what we want to read out. This is referring to the main that's currently around, and this is the data set which we've been accumulating, and we want to save it away into our data set. Okay? So, and we need a semicolon after it because we're saying accumulate it. Do this. We're not getting a value back. We're saying do this now. Okay? And then, ladies and gentlemen, before each experiment run, before we run the whole darn experiment, we're going to clear out anything that was in this data so we don't just, when we run the experiment once or run it again, we don't want it to, the whole experiment, which may run it 50 times, the particular main 50 times. If we run the whole experiment again, we don't want it to just accumulate more. So here we would do before each experiment run dot reset. And that's it. That's it, ladies and gentlemen. Okay? So, I have one error here. Okay. Oh, of course. Sorry, folks. I forgot the key word. Here, what you're doing is you're doing add. So we're adding in what we got from main to what's here already. So we need this dot add thing. It's not just calling it with it. We say dot add. Are we okay with that? Okay, so let me put it up on the big screen and see if I can explain it in other words. So here, we are keeping track in the experiment. So the experiment outlives main. Now the experiment is running main many, many, many times, like 50 times. For each of those runs, there's information accumulated within main in this data set that we added. Remember that data set? We looked at it. You could see the graphs. So within a given run of main, that's where the data is accumulated. Now, main has got to be run again. It's got to be reused. It's got to be destroyed and recreated every time. So before it's destroyed, we read out that data and we add it into this thing which is in our experiment. That thing right up there, that D at the top of my finger, up there. We're taking the data from main and we're storing it away in our summary information. And that's why it's dot add. Okay? Are we okay with that? So let's try running this thing. Let's try running it. Okay? You'll notice that it has this kind of odd coloration, which we'll explain in a minute. But I'm going to run it. Okay, so now it's running it many, many, many times here. Okay, and you'll notice that up here, Okay, now this is interesting. Okay, so this is the information, but there's a wee bit of an issue here, which people may notice. We're not seeing any data appearing, and there's a reason for this, and it's a common mistake. The reason is that what we see is the axes are off of what we want, okay? So we are seeing that the y-axis is from 0 to 1, but actually we're dealing with prevalent case counts, which are like 90 and 100, etc. So we're not actually accumulating things within the right range here. They're outside the range of the graph. So, and indeed of this data. So what we're going to do is we're going to go back here. Okay. We're going to go back and we're going to set in the plot here. Right. So in this plot, we're going to make sure that, and I think this is fine. I don't see a problem there, but it's really this one. We're going to set the x-axis range and the y-axis range for this 2D data object. Do you see that? So I'm still in the experiment. I went to this 2D data, and I'm going to set the number of intervals here be 1,000, and the x range will be from 0 to a time 1,000. The y intervals I'll set to be 250 from, I'll actually say 25 for reasons we'll see, from 0 to 250, because we have a population size of 250. Okay. 25 bins from 0 to 250. Each will hold from 0 to from up to sort of a range of 10. Okay. So here we're going to have bins, and each bin will count the number of times that it fell within that bin. Okay. So we're going to be counting this accumulation over different runs. Is going to count the number of times at a certain time the model had a certain number of people infected. Okay? We'll talk about this in just a minute when we see the graph. So now I'm going to run it. So I'm running it, and here we run it. And for each run, it's going to accumulate. Do you see that? It's accumulating this here. Now, you'll notice that it's all seems, what's odd about this? It's a classic problem. What's odd? It's precisely the same. What does that make you suspect? It's not, it's using the fixed seed. So let's go. And this is the shocking fact. AnyLogic did change, I believe they changed this default at one point from random seed back to fixed seed. And for this case, it's particularly odd because we're actually doing it precisely to check the effects of stochastics. So we're going to change this to random seed. Did you do that associated with the parameter variation? Now let's run it. And now, ladies and gentlemen, it'll be running them in parallel. Save it away. And now the fox shows its tail. What do we see as a result? Can anyone comment? Are there regularities here? Are there things that transcend a particular run? Are there things that are sort of common to all runs? Give me list one thing that's common to all runs. Okay, the range. Yeah, we don't see some runs which go up to 250. We do see some, I don't know if you can see it on yours. Sometimes you have to treat your monitor, but there's a bit of fringe down here. There are a few that go down to 0, where it dies out. Okay, what's another regularity? Yeah, the start, you have these pronounced oscillations at first. After that, it's kind of a grab bag, isn't it? It's kind of a grab bag of things after that, where it's kind of in this range from about 70 down to about 30 or so, right? It goes in this range, but it isn't till about time, 150, that you start getting in this kind of, this regime of kind of near dynamic equilibrium. It's not equilibrium where it's in total balance and stasis. It's kind of oscillating, but it's oscillating in this range, and it, the exact timing of those oscillations is different. Hence, it's kind of fuzzy in here. But these initial oscillations, those are very regular quantities. You might not know it from one run, but you run it many times over, and you see this. Now, there's ways we could tweak this. I'll just note, for example, given what we saw, we really don't need to go up to 250 for the top. We could probably go up without adverse effects to 100, and maybe we'll make the number of intervals 50, make it a little bit larger, right? We might also want, you notice you can specify envelopes around the median here to capture sort of quantiles around the median for summary statistics. And you'll notice that in the chart, by default, it shows envelopes, not bins. If you want bins, you need to go to the chart and select show bins. That will now show, if you select show bins, that counts the number that have fallen in there, not the number that lay within that range. So in short, I went here, I set y-axis range to go to 0 to 100 instead of 0 to 250. I set the number of intervals to be 50. I went here and I said show bins. And, it did it fast enough. And it's showing it along the way that I actually could run this thing many times over beyond 50. I'm going to up it to 100. Heck, we're going to lunch. You could make it 1,000 if you wanted to, and go to town. And here we go. And in the final run of our session, you will see a thing of beauty. So here this is spelt a little bit more. We're accumulating over time. As it's accumulating, it's summarizing it. It's a bit finer grained, but once again we see these regularities. And we see this initial peak went up to 100, went as far down as looks like 5, and it did appear when I looked at it before that a few may have died out then. But once again, you see these regularities out to about time 150, and after that, it's kind of highly variable. 100 runs summarized, ladies and gentlemen, so we can secure more robust results. Now, that's all we have time for before lunch. I will just note that we'll take a quick look this afternoon on how when we vary a parameter value, how that induces big changes here. For example, it might change the timing of these swings, the frequency of the swings, how far up it goes. But all of that, the mechanism is in place now. All we have to do to examine that is go to our parameter variation experiment here, which is exploring, and change it from freeform to varied in range, and change these parameters to vary, from a minimum, for example, of 25 to a maximum of 1,000, and steps of 20 or something like that. And there we will be summarizing not over many runs of the same exact scenario, but rather runs where we have very different numbers of people in the model. Or we could do so, more commonly, we do so not with population size, we change that back to fixed, but with mean time till recovery, or mean time to loss of immunity. So if we change this, for example, to a range and did it from 10 to 100 in steps of 2, we could see the effects of changing that parameter assumption over the course of different runs. So that's all we have time for now. The buffet beckons, and we will go and have lunch, reconvene. Most of the afternoon is project sessions, but we will have a case study presentation as well from 3 to 4 that 2 of the TAs are working on. So thanks very much. I look forward to seeing you in the faculty club here, and we'll reconvene in an hour. I will put my model out immediately. Yes.
This was a video called SIR and something else, right?
Yeah.
Yeah.
Yep. Yep. And